Kubernetes. It runs Kubernetes in VMware. It runs basically everything. If you want to stream Windows desktop from a computer to your remote device, no problem. If you want to stream Omniverse, no problem. If you want to run your robotic stack, no problem. Just the QA of this particular machine is insane. The applications that it runs, basically universal. Everything the world's ever developed should run on here, including, if you're a video gamer, including Crysis. If you can run Crysis, you can run anything. Okay, this is the RTX Pro server, brand new enterprise system. So something is changing. We know that AI is incredibly important technology. We know for a fact now that AI is software that can revolutionize, transform every industry. It can do these amazing things. That we know. We also know that the way you process AI is fundamentally different than the way we used to process software written by hand. Machine learning software is developed differently and it runs differently. The architecture of the systems, the architecture of the software, completely different. The way the networking works, completely different. The way it accesses storage, completely different. So we know that the technology can do different things. At TSMC, Samsung, large semiconductor fabs. Before the chip is made, it runs through an inverse physics algorithm called cuLitho, computational lithography. Direct sparse solvers, algebraic multi-grid solvers. cuOpt, we just open sourced, incredibly exciting application, library. This library accelerates decision making to optimize problems with millions of variables for millions of constraints, like traveling salespeople problems. Warp, a Pythonic framework for expressing geometry and physics solvers, really important. cuDF, cuML, structured databases, data frames, classical machine learning algorithms. cuDF accelerates Spark, 0 lines of code change. cuML accelerates scikit-learn, 0 lines of code change. Dynamo and cuDNN. cuDNN is probably the single most important library Nvidia has ever created. It accelerates the primitives of deep neural networks, enabled artificial intelligence to come to the world. Our first contact was in 2012, just prior to that, working with developers on a new type of algorithm called deep learning. It enabled the AlexNet big bang of AI, 2012. In the last 15 years or so, AI has progressed incredibly fast. The first wave of AI was perception, for computers to recognize information, understand it. The second wave, which most of us were talking about the last 5 years or so, was generative AI. Digital twins that operate. And so today we're going to talk a lot about digital twins. Well, what started out as a GeForce graphics card, anybody in here know what a GeForce is? Okay, all right. Well, what started out as GeForce looks like this now. This is the new GeForce. It is 2 tons, 2.5 tons, 1.2 million parts, about $3 million. 120 kilowatts, manufactured in 150 factories. 200 technology partners working with us to do this. Probably something along the lines of $40 billion in R&D budget in order to create what is GB200, and now moving to GB300. It is completely in production. And this machine was designed to be a thinking machine. A thinking machine in the sense that it reasons, it plans. This represents one node of an AI supercomputer. About $500,000. This is the Hopper system. This is the system that really put us on the face of the map of of AI, and it was under allocation for a very long time. Memory semantics interconnect. It's a compute fabric, not a network. It directly connects to the CPUs of all of these different NVLink systems, compute nodes. This is the switch. 9 of these on this backplane. This is how you shrink the internet into 60 pounds. NVLink. And so we did all that. We did all that because the way a computer is considered, the way you think about computers is going to be fundamentally different in the future, and I'll spend more time on this. But it was designed to give Blackwell a giant leap above Hopper. Remember, Moore's law, semiconductor physics, is only giving you about 2 times more performance every 3 to 5 years. How can we achieve 30, 40 times more performance in just 1 generation? And we need a 30, 40 times more performance because the reasoning models are talking to them. Training capability might enhance it tremendously. We're going to do this generation after generation after generation. And so for all of you who use this Nemotron, you will know that there's a whole slew of other models in the future. And they're open anyway, so if you would like to start from the open model, that's terrific. If you'd like to start with the Nemotron model, that's terrific. And the Nemotron models, the performance is excellent. In benchmarks after benchmarks after benchmarks, Nemotron performance has top of the leaderboard all over the place. And so now you know that you have access to an enhanced open model that is still open, that is top of the leader chart. And you know that Nvidia is dedicated to this, and so I will do this for as long as I shall live. Okay? This strategy is so good. This strategy is so good that the regional model makers, the model builders across Europe, have now recognized how wonderful this strategy is, and we're partnering together to adapt, enhance each one of those models for regional languages. Your data belongs to you. Your data belongs to you. It is the history of your people, the knowledge of your people, the culture of your people. It belongs to you. And for many companies, in the case of Nvidia, our data is largely inside. 33 years of data. I was looking up this morning. Siemens, 180 years of data. Some of it written down on papyrus. Roland Bush is here. I thought I'd pick on Roland Bush, my good friend. And so you'll have to digitize that before the AI can learn. And so yeah, the data belongs to you. You should use that data, use an open model like the Nemotron and all the tool suites that we provide so that you can enhance it for your